This is a lesson about quadratic equations. More specifically, about solving quadratic equations. Quadratic equations are polynomial functions with a degree of 2. In other words, the highest exponent is 2, or it involves x squared. There are many methods for solving quadratics, namely graphing. When we graph quadratics, we find the solutions by looking for the x-intercepts. So here and here. Remember that x-intercepts are the value of x when y equals 0, and therefore x equals 1 is a solution. Over here, this is the value of x when y equals 0, and therefore x equals 4 is a second solution. In addition to graphing, we can factor the polynomial and then use the zero product property. We can also do something called completing the square. In completing the square, we hope to make the right side and left side of an equation a perfect square, and then take the square root of both sides to solve for x. Lastly, we can always use the quadratic formula whenever solving a quadratic equation. The quadratic formula is x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Hopefully all these methods are familiar to you. So first let's look at graphing. You can find the zeros on a graph by graphing the function and finding the x-intercepts. So here's one x-intercept. This is a 0 because this value of x, -5, makes the y value 0. Therefore, x equals -5 is one solution to this quadratic. Here's another x-intercept. When the value of x is -1, the entire function is equal to 0. Therefore, x equals -1 is a second solution. You can also find these zeros by plugging in the equation of the quadratic into your calculator. In this case, you could try plugging in y equals x squared plus 6x plus 5. Next, you can go to the Calc button and then select zeros. Doing that will help your calculator identify these two x-intercepts for you. This one and this one. Another type of method for solving quadratics is factoring and using the zero product property. Hopefully you remember that factoring is a process which takes an expression that's the sum or difference of terms and turns it into the product of two factors. In this case, the factors are x plus 5 times x plus 1. From here, we have to use the zero product property. The zero product property tells us that if two things multiply together and give you 0, then one or both of them have to be equal to 0. Makes sense, right? The only way to get 0 as an answer is to have one of the factors be 0. So we're going to take our two factors, x plus 5 and x plus 1, and we're going to set these two factors equal to 0. And now when we solve each of these, we get x equals -5 and x equals -1, and those are the zeros of the equation. Now I used the same equation that I used when I showed you the graphic method so that you can see we can solve once graphically, but we also have an algebraic method for solving quadratics. So other algebraic methods include completing the square. To complete the square, we have to make the left and right hand side of the equations perfect squares. So this should look like this, but it doesn't right now. So what we want to do is we want to make it look like that. And the way we do that is we take x squared plus 6x, and I'm going to move this -5 to the opposite side of the equation. And the reason why I do that is because I make room to add something to the left side of the equation so that this becomes a perfect square. Now, the way you do that is you take the middle term, which in this case is 6, or the linear term, and you divide it in half. So I'm looking at step 3 right now. B, which is 6, divided by 2 is 3. Then I square it and I get 9. Now if I add 9 to this side of the equation, I have to add 9 over here. Okay, so far so good. Now I've got x squared plus 6x plus 9. If you don't already recognize this, it's a perfect trinomial square, which is x plus 3 quantity squared. So I've achieved my goal. I've made the left side of the equation a perfect square. On the other side I have 4. Now to solve this, I need to look at step 5. Take the square root of both sides. I take the square root of the left side, I take the square root of the right side. On the left, the square root and the square cancel each other out, leaving me with x plus 3. On the right side, I take the square root of 4, and I get two answers, positive 2 and negative 2. Remember that the square root of 4, there are two solutions here, because negative 2 times negative 2 is 4, but also 2 times 2 is 4. So what do I do with this? Well, I have one answer that looks like this, x equals negative 3 plus 2. And I have one answer that looks like this, x equals negative 3 minus 2. Here x is equal to negative 1, and here x is equal to negative 5. I hope these look familiar because they're the same two solutions we got when we factored and used the zero product property and when we graphed this equation. So we've solved for x, and this is completing the square. Okay, so the next thing we want to look at is the quadratic formula. Now I've intentionally chosen a different equation to show you the solution of the quadratic formula here because there's a couple of things we have to talk about for the quadratic formula. And namely is that the quadratic formula requires you to know A, B, and C. So when you look at the formula, there are variables here, right? B and A and C, and those variables correspond to certain parts of a quadratic equation. And you may not see those parts until you put an equation in standard form. So the way we're going to do that is we're going to write the leading coefficient with the highest degree first. This guy is always A. A is the coefficient of the quadratic. Then we're going to write the linear term. B is always the coefficient of the linear term. Then we're going to move the constant over so that our quadratic is equal to 0, and C is going to be the constant. Now I can't use A, B, and C until I have my quadratic in this form. So make sure you always set it equal to 0, and you always choose A for the quadratic, B for the linear, and C for the constant. And now I can substitute these values into my equation. I get x equals minus b, which is minus 3, plus and minus the square root of b squared, which is 9, minus 4 times a, which is 2, times c, which is negative 5, all over 2a, which is 4. So I get x equals minus 3 plus or minus the square root of, now 9 minus a minus 40 is 49, all over 4. This becomes x is equal to minus 3 plus the square root of 49 over 4, and x is equal to minus 3 minus the square root of 49 all over 4. And I get x equals 1, and x equals minus 10 over 4, which is minus 5 halves. So these are my two roots or solutions to this problem. Okay, now that we've looked at the quadratic formula, let's take a look at a problem like this. The height of a rocket after launch is modeled by this equation. I hope you notice that this equation is a quadratic. And I can tell it's a quadratic because the highest exponent here is 2. So this problem is asking me to find out when will the rocket be 114 above the ground. So h is equal to height. 114 equals minus 16t squared plus 232t plus 2. Now remember that I can't solve this until it's equal to 0. So I have to subtract 114 from both sides. And 2 minus 114 is negative 112. Now from here, I'm going to go back and I'm going to use one of those four methods. I'm either going to graph, try to factor it and use the zero product property, use the quadratic formula, or complete the square. In this case, it might be easiest to just use the quadratic formula. But once you have any problem in this form, you can always use one of those four methods. Now, it's helpful to talk about something called the discriminant, because the discriminant is another way of deciding which of those four methods is best for solving my problem. Now, what is the discriminant? The discriminant is the part of the quadratic formula that's underneath the radical, right here, b squared minus 4ac. Why is b squared minus 4ac such an important part of the quadratic formula? Because whatever happens underneath the radical makes a big impact on what kind of answers you get. So let's look at some different cases here. Now imagine that the discriminant is negative. Well, what happens when you put a negative under a radical? Well, you're going to have no distinct real roots. Okay? So if I don't have any real roots, because I can't take the square root of a negative, then that means I'm going to have two imaginary roots. All right, so let's say that now this time the discriminant is 0. So imagine that you come over here and this part is 0. What happens when you take the square root of 0? Well, that whole part of the quadratic equation disappears. And because that disappears, there's no more plus and minus, and we just get minus b over 2a. And then there's exactly one root. Now you can see from the first problem, if the discriminant is less than 0 and I have no real roots, then of course I have no x-intercepts. So graphing is another way of telling you what your solutions are going to look like. If I don't have any x-intercepts, then I'm going to have imaginary roots. Now if I have exactly one rational root, then it will touch at exactly one point. Okay, so this is one intercept. That's a 1. Okay. Now if d is greater than 0, and I'm taking the square root of a number that's greater than 0, I'm going to have two distinct real roots. And what that means is that my graph is going to pass through the x-axis 2 times 2 x-intercepts. Now if it so happens that, and this is a special case here, if it so happens that when I look for the discriminant and it's not only greater than 0 but is a perfect square, then my roots are going to be rational. And anytime you have rational roots, that means that it's factorable. Now, if I have a problem that's factorable, then I'm probably going to factor and use the zero product property as my method for solving. Graphing is going to be difficult if your numbers are not whole numbers, right? If you're looking on a graph and you're trying to find the x-intercepts, it's hard to see if the x-intercept is negative 1.56789. But if your discriminant is a perfect square, then you can count on your roots to be rational. That means they're either whole numbers or fractions, and those are not that hard to see on a graph.